set partitions. Now assume that the balls are different, but the boxes are not. Then we might as well label the balls by numbers 1 through n. In other words, we may simply say that we want to partition the set embraces into k non-empty subsets. Definition 5.5. The number of partitions of embraces into k non-empty parts is denoted by S of nk. The numbers S of nk are called the Stirling numbers of the second kind. It follows from definition 5.5 that S of nk is equals to 0 if n is less than k. We said S of 0, 0 is equals to 1 by convention. In the next chapter, you will see an advantage of this convention. Until then, be comforted in knowing that there is one way to distribute zero objects into zero boxes, namely by not doing anything. The parts of a partition of embraces are also called the blocks of that partition. Example 5.6. For all n which is greater than or equals to 1, we have S of n1 is equals to S of nn is equals to 1. For all n which is greater than or equals to 2, the equality S of n(n-1) is equals to n choose 2 holds as a partition of embraces into n-1 blocks must consist of one double term and n-1 singletons. Example 5.7. The set 4 braces has 7 partitions into 2 non-empty parts, namely 1, 2, 3, and 4, 1, 2, 4, and 3, 1, 3, 4, and 2, 2, 3, 4, and 1, and also 1, 2, and 3, 4, 1, 3, and 2, 4, and 1, 4, and 2, 3. Therefore, S of 4, 2 is equals to 7. Several questions are in order. The reader may wonder what happened to the Stirling numbers of the first kind. These will be discussed in Chapter 6. The reader may also think that the first thing we will do is to provide a formula for S of nk and may in fact wonder why we have not done it yet. However, there exists no closed formula for S of nk. There is a formula for S of nk that contains one summation sign, and we will prove it in Chapter 7 as we need the sieve formula to obtain it. Nevertheless, we can prove some nice identities about set partitions right now. They will be of a recursive nature. Theorem 5.8. For all positive integers k which is less than or equals to n, S of nk is equals to S of n-1 k-1 plus k times S of n-1 k. Proof as before, we can obtain a combinatorial proof by taking a close look at one particular element, say the maximum element n. If this element forms a singleton block, then the remaining n-1 elements have S of n-1 k-1 ways to complete the partition. These partitions are enumerated by the first member of the right-hand side. If, on the other hand, the element n does not form a block by itself, then the remaining n-1 elements must form a partition with k blocks in one of S of n-1 k ways. Then we can add n into any of the k blocks formed by this partition, multiplying the number of all our possibilities by k. These partitions are enumerated by the second member of the right-hand side. As the right-hand side enumerates all partitions of embraces into k blocks, the claim is proved. If we have to put n different balls into k different boxes, then the number of ways to do this is k factorial times S of nk. Indeed, first we can partition embraces into k non-distinguishable parts in S of nk ways. Then we can label the k parts with labels 1 to 3 until k in k factorial different ways. Corollary 5.9. The number of all surjective functions f which maps from embraces to k braces is k factorial times S of nk. Proof. Such a function defines a partition of n factorial. Such a function defines the partitions of embraces. The blocks are the subsets of elements that are mapped into the same element I, which is in k braces. Therefore, the blocks are labeled and there are exactly k of them. So the proof follows from the previous paragraph. An interesting consequence of this is the following unexpected corollary. It is surprising as it shows that x to the n, this very compact expression, is in fact a sum of n plus 1 terms involving Stirling numbers. Corollary 5.10. For all real numbers x and all non-negative integers n, x to the n is equal to the summations of s of n k times x with the subindex k, summing starting from k equals to 0 to k equals to n. Proof. Both sides are polynomials of x of degree n, so if we can show that they agree for more than n values of x, we will be done. We will prove an even stronger statement, namely that the two sides agree for all positive integers x. So let x be a positive integer, then the left-hand side is the number of all functions. From n braces to x braces, we claim that the right-hand side is the same, enumerated according to the size of the image. Indeed, if the image of such a function is of size k, then there are x choose k choices for the image I. Then, by corollary 5.9, there are k factorial times s of nk choices for the function itself. As x with subindex k equals to k factorial times x choose k, the claim is proved. Another way of extending our enumeration of partitions is by enumerating all partitions without restricting the number of parts. Definition 5.11. The number of all set partitions of n braces into non-empty parts is denoted by b of n, and is called the nth Bell number. We also said b of 0 is equals to 1. So b of n is equals to the summations of s of n I, summing from index I starting from 0 to I equals to n. The Bell numbers also satisfy a nice recurrence relation. Theorem 5.12. For all non-negative integers n, b of n plus 1 is equals to the summations of n choose I times b of I, summing with index I starting from 0 to n. Proof. We must prove that the right-hand side enumerates all partitions of n plus 1 braces. Assume the element n plus 1 is in a block of size n minus I plus 1. Then there are n choose n minus I, which is equals to n choose I ways to choose the elements being in the same block as n plus 1. Then there are b of I ways to partition the remaining I elements of n plus 1 braces, and the proof follows.